hack the bridge, right? So I guess I'll keep this kind of interactive. How many of you have like actually used a blockchain system, like Bitcoin, Ethereum, anything like that? A quick raise of hands. Okay. All right. So yeah, and I'm sure pretty much of you have heard of cryptocurrencies, Web3, right? That's all the hype, right? So because we do not have a big population of people who are familiar with the system, we'll go through the basics and then we'll get to the bridge. Okay? Awesome. So a little bit about myself. My name is Anto Joseph. I work as a security engineer at Coinbase. I've been a speaker and trainer at a couple of these conferences. And I love to be at NullCon. This, I believe, is my 6th or 7th time at NullCon. I love it here. Thanks to the organizers for having me. I am interested in distributed systems, as you can imagine. Other than computers, I also do some biotech. And I love to do some jet skiing and some rock climbing and DJing. Okay, so this is very, very important. I couldn't stress this enough. Because we are going to talk about money, this is not financial advice. Please, you should be really careful about this. You will share a lot of things in this talk, but none of this is financial advice. It is also not legal advice. These are purely my opinion and none of my employers. And this is only meant for educational purposes. So we'll be discussing some exploits and we will demonstrate them, but it's only intended for learning purposes. Okay. Blockchains 101, right? What are blockchains? So at the very basic, so we aren't going in depth, we are going broad. So at the very basic, it's basically a list of transactions that anyone can view and verify. So if you think of the Bitcoin blockchain, sending a Bitcoin to another party essentially means a transaction. And it's publicly available for anyone to see and verify. Now, Bitcoin allows you to like send and receive, right? That's awesome. And it has great properties. Now, can we do more with blockchains, right? And that's what Ethereum does. Ethereum allows you to have distributed compute on a blockchain. So instead of sending just value, like Bitcoin has some value, right? So if I send you some Bitcoin, I'm sending you some value. But can I also do compute? That is what Ethereum really solves. So it's also a distributed ledger, but it's also a computational platform where you can deploy code. So a way to like imagine this is you might write some code in like Python or like I don't know, Node.js or something, right? And you would deploy it to a server where people can access it. Now, if your server goes down, that's it. People can't access it anymore. When you deploy your code to like a blockchain, every node that runs the blockchain also has a copy of it. Hence distributed, right? And the execution of it, the computational integrity of the execution is guaranteed by executing the same code in all the nodes of a blockchain. So assume I have a calculator on my Mac. I can make 2 plus 2 equals 5 because the calculator runs on my laptop, right? I can just hook into the program and modify the output. But when I run the same compute on millions of computers, right, I cannot hack all these computers and like change the output. That is how the computational integrity of a contract, a smart contract, which is a piece of code that you would deploy to a blockchain, a smart contract blockchain like Ethereum works. And that is how they ensure the integrity of it. If at any point you have questions, please raise your hand, or at the end of it, we can have like 5 minutes to like talk about these questions. All right. So a very broad overview of what a blockchain looks like. A blockchain, the block in it basically you build blocks one after the other, and the previous block will reference the one before. And if you want to build a block after, so imagine block 10, right? If you want to build a block after that, it has to, it will be block 11, and it has to build on top of block 10. And that is how they ensure the chain. You can't just come up with a block and ask it to be a part of a blockchain. It has to follow a structure. Imagine it as a linked list. If you are into data structures, it's more like a linked list, right? And then we discussed that there are transactions that are part of a block. So you can see that in the middle, there is like a tree-like structure. It's a Merkle tree. So a Merkle tree is a data structure that you can use to like commit to a root, which is the Merkle root, and thereby ensuring the integrity of the transactions which are part of that Merkle tree. And we'll come and we'll talk a lot more about it in the other slides, but this is how a transaction root is arrived, and that root kind of attests to the integrity of all the transactions that are attest to the inclusion of transactions in that block. All right. So smart contracts. What are smart contracts, right? It is sometimes immutable. When smart contracts became a thing with Ethereum, they were not immutable, but now we have more smart contract platforms and they allow upgrades for smart contracts, hence sometimes immutable. And it runs on a blockchain like Ethereum, Solana, Cosmos. These are all different kind of blockchains, and they all have different guarantees. And they allow developers to build apps. The apps that you deploy on blockchains are called dApps. And they take advantage of the blockchain security that they offer, which is reliability, accessibility, and distributed execution. And you can have all sorts of apps built on blockchains. I think we see a lot of financial applications that are built on these blockchains. And they seem to have the most product market fit. We also have things like NFTs and like DAOs. So there is a lot of activity going on. And if you are interested in seeing what's going on, you can look at a block explorer like Etherscan, which allows you to like look at all the transactions and the activity that happens in a blockchain like Ethereum, for example. Now, what do these smart contracts look like, right? They just look like regular code. So on your left, you will see a bunch of code. The very one on the left is Solidity, and in the middle you have Rust, and then all the way to your right it's Go. So it's not something special. You probably know these languages already. It's just a way you write and think about these programs that are actually different. So you can. These are some of the popular smart contract programming languages. Solidity is used by the EVM or the Ethereum virtual machine, and then Rust is made popular by Solana, and then Go is made popular by the Cosmos ecosystem. All right, so I think the two most popular blockchains are Bitcoin and Ethereum, right? Imagine you have a lot of Bitcoin. That would be nice, right? Now, you want to do something with it. Sure, it's nice when the numbers go up, but what do you do with it? Like, you may want to lend, borrow, maybe get some yield. These are like normal financial applications that a bank would provide you with, right? So if you have some gold and then you deposit it with the bank, maybe you can take a loan against it. That seems reasonable, right? Can I do that with Bitcoin, right? You could go to like a crypto bank and do it. Then you would have to give them your custody of Bitcoins. if the bank gets hacked, that's it. There goes your Bitcoin, right? So that doesn't seem so great. Now, can I do this without trusting a centralized entity? Right? The idea of blockchains are all about decentralized and trust yourself. So kind of doesn't make a lot of sense if you are just going to go back to a bank. So the idea is maybe you can send some of your Bitcoins over to a network which has computation. Because to lend and borrow and to get some yield, you need to run some code, right? It's not just transactions anymore. There needs to be math involved. And then Ethereum is one such smart contract programming, smart contract blockchains where you can run code that is written in Solidity, and then there are other languages like Viper. So that's the idea behind bridging. Basically sending your tokens, which are native to one blockchain, over to the other blockchain. So another scenario, right? We have some Ethereum, like the native asset of the Ethereum blockchain is Ether, and you want to use it on Solana, right? How do you send it across? Because the native asset, which is Ether, is not something that you can transfer to a completely different blockchain. Because these blockchains, think of them as like walled gardens. You cannot take something out of it. And the asset, which is Ether, only exists within the Ethereum blockchain. So how do I even do this, right? Like I want to send my Ether or my Bitcoin onto a different blockchain, but that is not natively possible. But there is a requirement for it, right? There is a market for it. So that really gives rise to the blockchain bridges. So why would you bridge, right? Some blockchains claim they have like reduced transaction fees. So blockchains have a trilemma where if they were to like really make themselves fast, it won't be as inclusive. And when you are not really that fast, the block space that you have will be limited. And then you can't really make your blocks bigger because it will take longer to propagate, and then all the nodes in your blockchain won't be able to get it or can be synchronized to the head of the block. So reducing transaction fees is not as easy as someone turning a knob. There are repercussions to it. But still, there are blockchains that claim to be decentralized and have reduced transaction fees. And guess what? People like reduced transaction fees. So they'd want to transact in a blockchain where there is less fees. And some blockchains claim to be really fast. Like Solana, for example, has a speed of like 400 milliseconds or something like that. That is amazing considering what Ethereum block time is, which is around 12 to 14 seconds, right? And there are definitely advantages to like fast blockchains. Like an order book exchange on Solana can update at least every 400 seconds. Whereas if you have an order book exchange on Ethereum, it will only update every 12 seconds. So you can see a problem here. When numbers go up and the numbers on your blockchain is not that accurate or cannot be updated that fast, there is an arbitrage opportunity, right? So you can buy from here, sell over there, right? So there are reasons why you would use a particular blockchain over the other. And right now it depends on the application that you are interested in. And just like a blockchain, every other blockchain has their own killer apps. And sometimes you just want to use a killer app which is on a different blockchain, and then you want to send some of your money over to that blockchain so you can use it, so that you can pay for your transaction fees and interact with these financial applications, right? And we have a bunch more reasons why you would want to do that, but it's basically better UX and personal reasons. Right. So we know that there is no way you could send the native asset over to a different blockchain. Like you cannot send the native Bitcoin from the Bitcoin blockchain over to the Ethereum network. So how do bridges do that, right? So bridges basically give you a representation of Bitcoin on the Ethereum network. So I would have an address, like assume I'm a bridge, right? I'll ask people to like send me your Bitcoin, and then I will credit a representation of Bitcoin on the Ethereum network to your address. So this can be thought of like CDPs if you are from the finance world, or it's just a synthetic token. So blockchains with compute allow you to create tokens. And Ethereum has a token standard called ERC20s. Now, you can create a token that is a synthetic representation of Bitcoin. And one of the popular ones is called wrapped Bitcoin or WBTC. And it is custodied by BitGo, which is a company. So essentially, you send them your tokens, and they will send you wrapped Bitcoin tokens on an address that you specify on Ethereum. Now you have Bitcoins on Ethereum, right? There are different ways of doing that. The one I described is a very centralized way of doing that. And we want to move from centralized way of doing things to a different levels of decentralized way of doing it. Because decentralization is not really something you can measure, but it's a spectrum, right? Something can be more decentralized and some things can be less decentralized. So there are two types of bridges that blockchain networks majorly use. One is a cross-chain bridge, and the other is a multi-chain bridge. So what is a cross-chain bridge? So if you are sending assets to completely different blockchains, like going from Ethereum to Solana, right? That is a cross-chain bridge. They have nothing in common. So you are trusting something in the middle, maybe you are trusting it a little bit, but some of the examples of cross-chain bridges are like Wormhole and Nomad. And then you have like multi-chain bridges. So multi-chain bridges mostly deal with moving assets within an ecosystem. For example, Ethereum has scaling solutions like Optimism and Arbitrum. These are optimistic rollups. And what that means is they take the computation of the base blockchain, they do it off-chain, and then they commit the updates at certain intervals back to the base blockchain. So that is how you could scale blockchains. And Optimism and Arbitrum use an optimistic approach, which uses something called as fraud proofs. Or fault proofs, and these are just proof systems which basically attest to the computational integrity of the compute that they have done off-chain. Some other examples of multi-chain bridges include like Cosmos, which has IBC. Okay, so as a user, you are faced with this dilemma, right? Do I use a cross-chain bridge or do I use a multi-chain bridge? And we have opinions, right? In crypto space, we have a lot of opinions. And this comes from the co-founder of Ethereum. His name is Vitalik Buterin. So he must be onto something, right? At least I think so. So he believes the future of blockchains will be multi-chain and not cross-chain because there are security issues going cross-chain. So what are these security issues, right? I'm sure some of you have heard of 51% attacks, which is like the most famous attack if you Google Bitcoin or blockchain security, right? Because, okay, so what is a 51% attack? It refers to like a potential attack on the integrity of a proof of work blockchain. So Bitcoin is a proof of work blockchain. Ethereum is also right now a proof of work blockchain and is going through a process called the merge, after which it will become a proof of stake blockchain, but we'll get back to that. So when a single entity controls more than half of the hashing power of a proof of work blockchain, they can basically double spend or censor transactions. And using a 51% attack, you can reorg the chain. And what that means is you produce block after block on a blockchain, right? Because I have more compute power, I can create a chain that conforms to all the rules of that particular blockchain, but not release it, and I mine it myself. And then when I have enough number of blocks, I can just expose it to the nodes, and by the longest chain rule, because I have a lot more compute and a lot more blocks built on my attack version of this fork, that fork takes precedence over the legitimate blocks that have been built. So it's basically saying that the proof of work blockchains are as good as the amount of hash power that a single entity can control. So if an entity can control 51% or more, a lot of guarantees offered by these blockchains are toast. So this is the scenario that we are talking about. So a bridge, you can bridge like 100 ETH from Ethereum to Solana, and then you can swap. So these blockchains have applications that are similar to exchanges, where you can go from one token to another, right? So you could swap some Ethereum or Ether to like the Sol token, and then when the Ethereum blockchain goes through a reorg, the transaction that we have bridged over to Solana is no longer part of the main chain, because we used the transaction to send your funds from the Ethereum blockchain over to Solana. But because the blockchain went through a reorg, all those transactions were reorged out of that blockchain. It is no longer part of the Ethereum network. Because Solana is not part of Ethereum and it's a completely different blockchain, the state is not synced, right? So we try to sync it when you send the transaction, but after that, the base blockchain or the source blockchain went through a reorg, and these transactions are no longer part of that Ethereum blockchain, but you still have funds on Solana. So this kind of a scenario is called as a double credit. Now, basically by bridging, you have 100 ETH on Solana, 100 ETH on Ethereum, and the equivalent amount on Solana, right? Like in USDC. So this is one of the reasons why people say that the future of bridges is more multi-chain than cross-chain, because the state cannot be easily synced when there is a reorg and things like that. All right. So again, the market demands something else, right? There are different blockchains with different features. So we do want multi-chain bridges. And I do see that they have topped some leaderboards. So what is this leaderboard that I'm talking about? So this is the rect.news leaderboard, which basically tracks all the blockchain hacks that have happened till date. And you can see that out of this 11 protocols out here, 5 of them are like cross-chain, multi-chain bridges. And you will see that the amount of funds that were lost on every single hack. Like the very first one, I don't know, about $624 million were lost. And I would imagine that they have done something super secure because they are custodying that much funds, but it essentially was a theft of private keys. A typical problem. This has nothing to do with blockchains, right? You have private keys on a computer, you have to secure the computer. If not, someone will steal your private keys. Someone stole their private keys and took their funds. So before we secure smart contracts and all that, we have to first of all secure our keys. That is very important. This is a problem that we have in the industry. This is nothing new to blockchains, but the first attack is essentially a private key theft. It has nothing to do with smart contracts or anything like that. Okay. So we briefly spoke about this. Essentially, I wanted to say that wrapped Bitcoin is a centralized way of bridging where you are trusting an entity like Bitcoin. And we have other ways of doing decentralized bridging, which involves message passing. And these are of varying degrees of decentralization because you are trying to connect two different entities that have nothing in common. So you need something in between. And essentially, you need a way to pass messages from one blockchain to another. So this will be an off-chain system, something that will observe one blockchain and then make transactions on the destination blockchain. This will be like an off-chain system, like a script that runs on a server or something like that. So this is what it looks like. So you would send a message from a dApp. That messages get committed. This is from the origin chain. So you can think of this as like the Ethereum blockchain, where you are sending some Ether onto a different blockchain. So there are off-chain actors. You can think of this as like a script or a server that monitors for events on the origin chain, like a deposit was made, and then they do some validation, and then they determine if they should forward it to the destination chain. And if they decide to do so, then you will get your funds credited on the destination chain. This is typically how a simplified message passing bridge works. So let's dive into like where the bugs are at, right? So you might remember the leaderboard that I showed earlier. The number one problem for some of these bridges are how do you custody private keys, right? And you can see that the first hack, the Ronin bridge hack, was theft of private keys. And there is another bridge as well whose private keys got stolen and then, funds were taken. So this is a typical problem. I'm not going to go in depth. We all know private keys should be private, should be secured, yada, 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 right? Now, people are trying to improve that by using MPC. It is called multi-party computation, where you do not need to store the private key, but you have shards, and these shards can be combined to form a signature on a transaction and never the private key. So it's advanced cryptography that is used to sign on transactions without actually materializing a private key. And what that enables is if you don't have a private key, you are less likely to get hacked. And then the shards need to be combined either in a threshold fashion where you have like, a multi-sig kind of a way where there is a 2 of 5 threshold, or the MPC way, like a 2 of 2 shards has to come together to like sign a transaction. And there are also cryptography bugs that affect these systems. And some of the problems that we face with cryptography systems are bugs in the MPC protocol itself. So I have links to that. It will take a while to like really go into the depths of what these bugs are. But if you are interested, you can click on it. I'll share the slides later so you can like read about it. And we also have like bugs in like fault proofs and like zero knowledge proofs as well. So these systems are used to guarantee the computational integrity of blockchains. And if you have bugs in the cryptography of the systems itself, then we have bigger problems. And these are some of the off-chain components that you will typically see with bridges. The relayer just relays transactions across bridges, and then there is a validator, and then there is a watcher. The watcher essentially looks for any fraud, and if they see any fraud, they will stop the bridge. That's the idea here. So we are going to go deep into like some of the smart contract bridge hacks and what was the bug behind them. So there are operational issues. Just like how you would deploy some code, you have to have some clean DevOps to like deal with smart contracts. And one of the first bugs that I have over there is a bug where they forgot to initialize their smart contract. And when you don't do that, anyone can take ownership or like do bad things with it. So it's just like deploying something with no control over it until you initialize it properly. And that bug alone was reported by a security researcher, and he was paid, I believe, $10 million for it. So another thing I want to highlight is the blockchain world or the Web3 world have big bounties because you are securing money. And if you are interested in it, we can talk about it after the talk. Now, the second bug is you deposit some tokens in a source bridge, like where you're bridging from, and then you mint tokens on the destination bridge, right? So in this attack, you don't have to deposit anything, but there is a bug in the destination smart contract where you can just mint these tokens that are a representation of Bitcoins on this destination blockchain. And when you do that, these bridges are not backed one-to-one, and then you can just like unwrap these Bitcoins, and now you have custody of Bitcoins, and the bridge is under collateralized. So what that means is the bridge is no longer backed one-to-one, which means all these synthetic tokens are of zero value now, or like reduced value. We also have like toxic privilege combination attacks where a smart contract that a user would interact can be used as a proxy to like call privileged contracts because of the proxy functionality that the user has. And because it comes through this proxied smart contract, the privileges of that smart contract gets transferred to that call, and using those elevated privileges, you can like add yourself as a validator and then like sign invalid roots or something like that. Then we have typical bugs like input validation and bugs within the logic of the smart contract itself. So these are like $1 million, if not $1 billion hacks that have happened. I have links to all of them, and it takes a good amount of time to go through one of these. So we're gonna actually do some actual exploits and see how they work and run through some code, and then we'll come back to some theory, right? All right. So the first bug that I'm going to talk about is a multi-chain bridge. So a very simple way of making a bridge is you have some off-chain components, you have some smart contracts, and that's it. You have a bridge, right? So let's look at the multi-chain bridge hack. So as I described, a multi-chain bridge over here uses some liquidity pools, and what that means is like you can, on the source blockchain, swap the tokens that you're interested in with the synthetic tokens that they have, like the bridge has, and then on the source blockchain, or sorry, on the destination blockchain, swap it back to the asset that you really want, or the synthetic version of it. So we'll actually run through the exploit and then explain what the bug is. All right. So this is the exploit for the multi-chain bridge. So this is a link to the block explorer, which has an exploit transaction, and we are basically trying to reproduce that. And this is written in Solidity. Okay, it's not a lot, so we'll look through what this is. So all right, so looks like something happened. So you can see that before this exploit, the attacker had 0 ether as his balance. But after I ran this exploit, the attacker's balance is this much. So, and we will have this exploits in GitHub, so you can run this yourself. But you can see that the exploit does make some calls and essentially drains the balance of the bridge. Right? The bridge secures a lot of money, and because of this exploit, we can take that money for ourselves. That is essentially what happened. And we'll look through how exactly this exploit works. So this is just like setup code, and this is just interfaces, which is like ABI. And the meat of the attack is over here, the test attack function, right? So we are calling this method, which is the vulnerable method, on the smart contract. And then you can specify the from address, the token address you are interested in, the address to which the funds should be credited. So basically follow this. And the bug here is so the attacker controls the token parameters, which is in turn used by the bridge contract to identify the underlying token. So because I can specify the address, the smart contract address that they're going to use, I just write my own smart contract. And instead of using the bridge's smart contract, I use my smart contract, which will return wrapped ETH as the token address. You can see that in the exploit here. You will see that the underlying does return wrapped ether, and as a result, this code looks at wrapped ether as so it calls the permit function on the wrapped ether contract, and this permit function doesn't exist on wrapped ether. So it just continues execution because it doesn't revert. And then, because these token bridges have unlimited token approvals, you can basically take the tokens that a user has already approved this bridge for using this exploit. And that is essentially how this exploit works. We also have one more demo. And this is the exploit for another bridge called the Nomad bridge, which is similar in many ways to this bridge, but it uses a very different mechanism. So we'll run the exploit, and then we will look at how the exploit works. So it looks like that worked as well. So you can see the balance before was 0, and then the balance after the exploit was a lot more, right? So let's look at how that works, right? So this is the function that we just executed, which is the meat of the exploit. And as before, we are essentially copying contents of a exploit transaction and replacing the address with the attacker's address. in that exploit transaction and then sending it across. So how does, what exactly is the bug, right? So the bug itself is, so this is how the contract was initialized when it was first deployed. And you can see that the committed root is set to 0 during initialization, as you can see down below, right? The third argument is 0. Then the replica contract, which we were looking at, was upgraded recently, and they changed how they would verify if a particular route was acceptable from what you see on the left. So what you see on the right to what you see on the left. So it moved from a comparison to like a lookup. And in Solidity, when you call an item that doesn't exist in a map, it returns 0. So the code essentially becomes acceptable root of 0, which maps to 1, which does exist. And basically what that means is this bridge accepts invalid routes. So you would have to submit a proper Merkle route for you to withdraw and transact. But because of this bug, you can essentially send it any invalid routes and then claim funds. And when that happens, this is really what happens to the bridge. Everyone takes the funds of a bridge, and now the bridge is asking for people to like return the funds. They were drained for a lot of money. I think this was like the third or the fourth biggest bridge hack. Right. So yeah. So what do we do, right? Like there is a lot of ways to like hack these bridges. So for developers, go through these verification standards, use audited libraries, first year contracts. So these are things you could do and write some invariant tests, and you will have a safer smart contract. And for white hats, for folks who are interested in hacking these projects or getting started in blockchain security, these are some of the tools that you could use. I will share these slides later so you can actually, click into these and like go explore, right? Yeah, so I think do we have time for questions? Yeah, okay. So we have 5 minutes for questions, and these are some of the references that I used. And thank you all for coming.
Does anyone have any questions?
Hello.
Yeah, hi. So it's a great talk. Thanks for that. So you said that it's the decentralized Ethereum. Then who decides the transaction fees?
Okay, so transaction fees is more like a function of the demand for the block. So block space is a very limited commodity, right? Like you may have like 1 MB or like maybe 10 MB, and a lot of people want to get into that block because sometimes your transaction is time sensitive. Now, when a lot of people compete for a very scarce resource, right? That is when you have the transaction fees go up, which is a rule that is written into the network. So it is part of the node software that you run, and it is basically a function of what is the demand that you have right now, and you can, as a user, specify how much you are willing to pay. So if your transaction is not really that time sensitive, you can still send it, but it will take a while for it to get mined into a block and get confirmed. And it is essentially a function of what is the demand of the block space right now versus how much you are willing to pay. Yeah.
Thank you.
Yeah.
Uh, Forgive me for asking a really noob question, but can you explain re-entrancy like I'm a 5-year-old?
Right. Reentrancy is, think of it as, okay, very abstract way of saying it is like URL redirects, right? So you would want to go somewhere, but then it redirects you to like something else, right? And when it redirects you to itself, especially when you're dealing with code that has a lot of state and manages financial value, you can use reentrancy to like and enter the smart contract again. So assume you are making a smart contract call, right? A call is a function that you can use to like invoke other functions in a contract or do things like that. Now, when you use a call, you can call yourself and an exploit would look like deploying a contract that the vulnerable function or the vulnerable contract would call, and then it would probably go to the fallback function, and the fallback function would call back into your contract, and then you can like maybe continue to like drain funds while your state is not modified, because imagine your state is like your balance, right? So this like in a vulnerable contract you would first of all, you will reduce the balance after the call has been completed, right? And that is a vulnerable pattern. You should probably do that upfront. Now, when you don't do that, you can choose to like loop through this and then drain all the funds, and only then the actual state update would happen. So it's more like a logic bug, and sometimes it can be cross contracts, it can be the same contract. So there are different varieties of exploiting reentrancy. We can talk more about it like maybe after. Yeah.